So, of course, you already know semantic memory is sort of our life experiences. Sorry if you guys wanted to listen in on that phone call out there. So semantic memory is our knowledge. It's acquired, of course, through our life experiences. It includes our vocabulary, knowledge about geography, all sorts of other things. So this is our permanent store of world knowledge. Of course, different from episodic memory in that there is no representation of time or context, and that's the thing that separates semantic memory from episodic memory, is it's completely decoupled from time and place. So we have no contextual information about when or where or even how we really learned this information. It's simply part of what we know. And over time, oftentimes, we even start to lose some of how we know what we know. So for example, as you get older, it gets much harder to explain math to people because you forget exactly how it's done. You just know how to do some of it. So some of the stuff that you may have learned long ago that had more context to it starts to disappear over time. So these are examples of different kinds of semantic memory. It's capital Colorado. How many legs does a typical horse have? I guess I should say. What color is a canary? These are basic bits of information we just have stored throughout the brain. What we're going to talk about today are some sort of models of how this information is represented. That is, exactly kind of what is the nature of how semantic memory is stored, how is information connected to other information, that sort of thing. So these are the key questions we have in terms of semantic memory. How is this information stored? What's the sort of nature of this representation? How is it learned and how is it retrieved? These are kind of some of the key questions. This is an ongoing, as everything in this area is, trying to figure out exactly what is the nature of semantic memory. How does it get formed? What's its relationship with episodic memory? Most of us believe semantic memory starts out as episodic and then eventually becomes independent of its context. Exactly how that happens is certainly something that's under investigation. The nature of the representation of information is interesting, and probably the most of this, how is information stored and how is it represented, is probably the most well investigated, and that's what we'll spend most of our time. We think, again, it's learned sort of through episodic memory and then eventually becomes independent of its context. And how is it retrieved? Part of the ongoing part of this analysis. So typically, of course, we have some new terminology to get out that's related specifically to semantic memory. First are concepts. Concepts are mental representations. This is often referred to as the fundamental unit of thought. This discussion tends to get a little esoteric in terms of how we describe these things. Doug Bedeen describes a concept as an idea that includes all that is characteristically associated with it. So when we're talking about something like a bird, that is a concept, and everything that's associated with that concept would be things like it has feathers, most of them can fly, that sort of thing. So a concept is this kind of fundamental unit of thought. They're represented by what we call nodes in semantic network, and that's what we'll talk about here in a moment. The other part of semantic memory are propositions. Propositions are relationships between concepts. So these are things like a canary is yellow. So canary and yellow would be the concepts. The relationship would be that proposition. A canary is a bird. These is-a propositions. I told you this gets esoteric and slightly weird when I talk about it. An is-a proposition is something like a canary is a bird, a chicken is a bird, a dog is a mammal, a poodle is a dog. bird has wings. This would be what we call a property proposition. That is, all birds have wings. We'll get into logic later. But certainly all birds have feathers. So these are property propositions. So a canary is yellow would also be kind of a property proposition. This starts to become important as we start looking at how information is represented, because we have to figure out where these property and sort of is-it propositions are related. So a bird is an animal, canary is a bird. So we'll start to look at how fast we can identify these concepts based on how closely related they are to one another. So for example, a sparrow is a bird is something that people verify as true very quickly, versus a chicken is a bird is something that takes them more time for people to verify that as being true, because we don't tend to think of chickens as birds. We tend to think of chickens as farm animals, or delicious, or nuggets. So we don't generally tend to think of chickens as being birds. They tend to be associated more with food and farm animals, whereas sparrows, canaries, parrots, they tend to be more closely associated with the concept of bird. Similarly, penguins are less associated with being birds, ostriches, because they're just so different from our concept of birds. And that becomes important when we start thinking about how we represent this kind of information. So the first thing we're going to look at is what we call the Collins and Quillen hierarchical model. This is a model of how semantic memory is stored, how it's represented. When we talk about these kinds of models, they both describe how we are probably accomplishing this kind of information, and oftentimes these models are often represented in computer models as well, so we can predict behavior based on how a computer is responding. So the first thing to understand when we talk about these models is they're all what we call network models, where we have interrelated sets of concepts that help represent our body of knowledge. So contained within these networks are nodes, and a node is simply a point or location in the network that represents a single concept. So when we talked about a canary is yellow, canary and yellow would be individual nodes in the network. So nodes represent concepts, and pathways are associated with propositions. So these are connections between propositions that tend to be directional. A canary is yellow, right? That would be directional. A canary is a bird. That would be directional. A bird is an animal. So the network is constructed based on nodes and pathways. Nodes represent individual concepts. Pathways represent the connections between concepts, particularly what we call these propositions. So these pathways represent these kind of connections between nodes. Why these are often called connectionist models. So we have a network consisting of nodes and pathways. We have ISA pathways that denote category membership. Well, a canary is a bird is an animal, something like that. So you can even get further down into properties. Poodle is a dog is an animal. Property pathways describe properties of concepts. So these property pathways are: a canary is yellow, a bird has feathers, a bird has wings, birds lay eggs. These kind of properties are associated with all parts of a particular concept. These become important distinctions because of the way these networks sort of are laid out. So you have to kind of understand these different kinds of property pathways and ISA pathways and how they denote different category memberships and property pathways. Because this is a hierarchical model, but it's easier to sort of show you how this works. So the way this is all put together is so we have this category of animal. So all animals have these particular properties. Skin, can move around, they eat, and they can breathe. Probably reproduce, can be another thing, but it's basic idea here. So then we have the category of birds. They have wings, can fly, and have feathers. This would be a typical bird. Typicality is an important part of this. What's important about the Collins and Quillen model is that bird inherits all of the properties of animals. So we know that birds have skin, can move around, and eat and breathe because they are an animal. Similarly, when we get down to canaries, there may be different kinds of canaries. Not being an ornithologist, I couldn't really tell you. But it would inherit then all of the, well, certainly chickens, for example. There's a bunch of different kinds of chickens, we know that. Would inherit all of these properties. Has wings, has feathers. This is where we start to get important. So we get over here to ostrich. Because it's an exception to this can fly rule, ostrich then we have to say can't fly because it inherits all of the properties of bird. Right? We know ostriches can't fly, they just run. And so each subordinate category inherits its sort of superordinate category. So if we go over here to fish, fish have fins, can swim, they have gills. Sharks can bite, not really all that dangerous. Salmon, but of course this is probably represented in most people's knowledge. Salmon is pink, edible, swims. I mean, sharks are edible too, but most people don't eat them. So this is a basic way in which we can store lots of information by making it hierarchical in this way because it's more efficient. So we don't have to store the fact that birds, dogs, cats, my dog, your dog, this particular cat, that bird out there, all of them can breathe because we know all animals can breathe. And so we just keep that information in one location. So it's a really efficient way to store information. The other important part of the Collins and Quillen model is this idea of what we call spreading activation. And what happens is when we access information in the network, activation spreads out to nearby nodes. So it spreads from one concept to another. So the mental activity of accessing and retrieving information from the network takes passive concepts, those not currently in working memory, and activates them. So I activate the concept of bird. It's going to spread to sort of nearby associated information with the concept of bird. Feathers, flying, chirping annoying noises outside your window, 6 o'clock in the morning, whatever it is you think about birds, all sort of spread to that information. So activation then spreads to related nodes. So if I activate the word doctor, it's going to spread to nurse, physician, surgeon. Which, by the way, this phenomenon of spreading activation is what causes that false memory phenomenon we saw in class. So we did that Schrodinger-McDermott list where I read you a bunch of words related to the word doctor. The fact that activation spreads to the doctor node and activates it in working memory is what causes you to misremember the word doctor being read from that list. So this is actually part of the explanation for that Schrodinger-McDermott paradigm we talked about earlier in the semester, is this phenomenon of spreading activation. This also allows us to empirically test the model, because if activation has spread to nearby nodes, they should be more active, and you should be faster and more accurate at identifying information associated with those nearby related nodes. So that's an important part of how we try to test out whether or not this information is, these models are actually accurate. So some key features of this particular model, it is hierarchical. That is, concepts are arranged in a hierarchy. Bless you. It becomes important because this allows for cognitive economy. Because it's much more economical. We don't have to store all kinds of redundant information by storing this kind of information in superordinate hierarchical categories. So all animals inherit the properties of breathing and reproducing and walking around and moving. So we don't have to add that to birds and dogs and cats and whatnot. We also have some assumptions, I should say, about this model, is that it takes time for activation to spread across inactive nodes. So it takes longer to access inactive information than it does recently activated information. So activation spreads more quickly across recently activated nodes. What that means is we can test this model by seeing how quickly people can verify properties like bird is an animal, or identify something as being incorrect, like a fish is a bird, something like that. Fish can fly. So we use these kind of statements to kind of measure how quickly information has spread and whether or not information has spread recently. By looking at things like priming, repetition priming, and how quickly we can verify these sentence verification tasks. So basically, people respond whether or not a property statement or some sort of statement is true or false, that sort of thing. So, this is an example of what might happen if we activate the concept of robin. We might activate this sort of level of information. So red-breasted robins, they have blue eggs. These would be property statements. We also know that robins are birds, so robin is a bird. This might activate the concept of canary, feathers, flying, animals, breathing, etc. So it kind of spreads out across the network. So the more closely related a concept is, the faster we should be at activating information. So if I ask you if a robin is a bird, and then very recently after that ask you if a canary can sing, you'll be faster because that information is spread to that nearby node. So that's the Collins and Quillen model. This is a kind of semantic network model. I want to talk to you next about Smith's feature comparison model. This is a little bit different. We'll talk about its kind of general structure. Smith's feature comparison model, its general structure is information about concepts are represented in feature lists, so it's not quite as connectionist as what we've talked about. These lists include both defining features and characteristic features. So I want to present a couple of these models, and then we'll kind of compare them and how they've held up. So according to Smith's feature comparison model, defining features are essential to the meaning of a concept. So it is something that is essential to defining that particular concept. A characteristic feature is a common but not essential to the meaning of a concept. So a defining feature for birds is that they have feathers and wings, whereas a characteristic feature of a bird is that they can fly. Most birds can fly, not all birds can fly, right? And so when we think about birds, we tend to think about birds that can fly, and then penguins and ostriches, and I mean chickens can't really fly either. I mean they can fly a couple feet, but you know they can't fly across the country. So the defining characteristics versus characteristic features are very, important parts of this particular model. These are captured in the model we just looked at by defining features being most closely associated with a particular category, and characteristic features are also more closely associated with that particular category. And then we just simply make the exceptions part of the individual concept. So a characteristic feature like can fly, when we get to chickens, we put, can sort of fly. Or when we get to penguins, can't fly. So we have to kind of make exceptions, those characteristic features in the other model, whereas here they're laid out in these defining versus characteristic feature lists. So this is the general structure of Smith's feature comparison model. Basically what happens in this model is we make matches between sort of defining and characteristic features and decide whether or not something fits into a concept. So here we have sort of defining features of a robin. They're physical objects, they're living, animated, feathered, red-breasted. The list of defining features. Whereas characteristic features of robins would be that they eat worms and roost in trees, but not necessarily. They might roost somewhere else, or they might eat something else. So that's an example of this defining versus characteristic features. Let's get other kinds of concepts. Zodiac signs are defined by their when you're born. It would be the defining features of whether or not you're a Leo. Characteristic features, I pulled this somewhere off of some internet website. I didn't just make these up just because I happen to be a Leo. These are the sort of characteristic features people associate with the zodiac. I'm not a believer in the zodiac. I'm not trying to make you think that. Just give you another example of how this kind of defining versus characteristic feature might work. So features are stored starting with the most defining, followed by the most characteristic. So we kind of store these things based on the things that are most closely associated with the concept. It's defined in this particular model by its position in these feature lists, whereas in other models they're defined by the distance of those pathways. So in the Collins and Quillen model and other models, we look at sort of distance across pathways as how closely something is associated, whereas in this particular model it's its position in this kind of list. And we compare these feature lists to make the kind of information that we need. So this is a comparison of these two kinds of models. So we have this attribute or feature list model. So we have these lists that are associated with birds, and these lists that are associated with robins. So we make a comparison and say, yes, a robin is a bird. Whereas in the hierarchical network model, we just know that a robin is a bird. We don't have to make this kind of comparison to decide whether or not a robin is a bird or not. So the first thing about these two approaches to semantic memory that you should probably notice is one has a much greater amount of efficiency built into it than the other. So in this case, we have a lot of redundant information being stored about information. So when we start looking at these different kinds of models, we tend to test them using what we call a sentence verification task. So you simply verify whether or not this is a true sentence, like robin is a bird. So according to Smith's feature comparison model, the model begins with a stage 1 comparison, which is a global feature comparison, where you get fast yes responses. This occurs when there's a large number of shared features. So we do this global comparison, a lot of features in common, we say yes, a robin is a bird. So that would have happened because pretty much all of the first features associated with robin were all of the first features associated with bird. We get a fast yes. We get a fast no when there are few shared features. So for example, a trout is a bird. Well, we would have a physical object that's animated, but then nothing else would match, right? It doesn't breathe, it doesn't have feathers, etc. Certainly, we would get an even faster no if we asked if a rhododendron is a bird. No, it's not animate. No, it has no features. No, it doesn't breathe. It doesn't do any of those things. So to get back to this, we'll come back to this slide here in just a sec. We look at this. We have a great number of shared features for robin versus bird, so this will be a fast yes. So we get a fast yes or a fast no, depending on the number of shared features. Now, if there are some sort of intermediate number of shared features, we move on to stage 2. So we get this comparison of defining features. So now we have to go a little bit further because we can't get a fast yes or a fast no out of the model. So we have to move on to something more advanced to try to decide whether or not the sentence is true. So we go on to the stage 2 comparison of defining features. This lists something like this. At this global feature comparison stage, we have a very low score in this feature overlap. We say no. Fast yes, robin is a bird. So if we get some sort of intermediate score, so a chicken is a bird is something we get a slow yes out of, versus a bat is a bird, we get a slow no. We have to go on to this defining feature stage in stage 2. So when defining features match, we get a slow